The Drake equation is arguably one of the most famous equations in the world, created by Frank Drake in 1961 to estimate the number of active, communicative, extraterrestrial civilizations in the Milky Way galaxy. The equation summarizes the main concepts which scientists must contemplate when considering the question of other radiocommunicative life. We have been filling in some of these values in the equation as we get more and more data, and while it's been a good guide up to this point, there's something missing. A missing value that would change everything. The Drake equation consists of 7 values that represent n, the number of civilizations in the Milky Way galaxy with which communication might be possible, i.e., which are on the current past light cone. The light cone, of course, is how far out we are able to see with our current technology. There is a barrier in which we will never be able to see, again with our current technology, because of the limitations on the speed of light, and if the expansion of the universe is true. Many of these values we are continuously learning about, like the rate of star formation. Over the years, we are gathering more and more data on how many of those stars have planets. To this date, we have discovered the existence of more than 5,000 exoplanets orbiting distant stars. And this has all been done in the past 20 years or so. And it's hard to believe now, but the scientific community would not admit it believed there were other planets until we verified and discovered these exoplanets. Out of those 5,000, 55 of them are said to be Earth-like, where they have enough mass and orbit their sun in a Goldilocks zone of those stars. The Goldilocks zone being the area of habitability. Based on data from Kepler and other planet hunting telescopes, astronomers estimate that there could be anywhere from 300 million to upwards of 40 billion Earth-like worlds in the Milky Way. So we currently have a good estimate of the fraction of stars that have planetary systems, and we're beginning to gain data for the value of the number of planets with an environment suitable for life. However, it is at this stage of the equation that we run into problems, for we are only now getting the ability with the James Webb telescope. There are even many variables within this, as many of the planets we can observe orbit around a red dwarf star in small orbits. These stars give off less heat and light than our star, and the close orbit allows the planets to be in that star's Goldilocks zone. But these planets, being so close, are tidally locked, meaning that only one side of the planet ever faces the sun, leaving one half bitterly cold and one half blazing hot. And questions remain on whether these planets can even maintain an atmosphere. Until we are able to see Earth-like planets around a G-type star like ours, we won't know for certain the more precise value for potential Earth-like planets that have conditions like that of our planet. But if we go off our estimations, we can use the Drake equation to say there are potentially X amount of civilizations out there. If life is found to be common, then it is reasonable to conclude that other entities out there will evolve into a technologically capable civilization. And this estimate has been for decades assumed to be much higher than what we observe, and what we observe currently is nothing. Just a dark, cold, empty of life void. Of course, this flies in the face of what we expect. We expect to see all sorts of life out there and other civilizations. We expect radio communications and evidence of a full of life galaxy and universe. But we don't, and we can't understand why. Theories of why we don't falls under the Fermi paradox, and there's quite a few of these theories, such as a prison planet, where a galactic federation has put us on this planet and we are quarantined and kept from the rest of the peoples of the galaxy. And another offshoot of that is the zoo hypothesis, where we are left untouched outside of scientific observation. The other civilizations, again, purposely hiding themselves from us so that we are not interfered with in our development and evolution. And the theories go all the way to either we are the last and only civilization, or the first civilization to reach this technological level that we have. Our first video was about this Fermi paradox and why it isn't a paradox at all. and why it's most likely we haven't heard from anyone out there. Mostly we talked about the distance between these possible civilizations, such as maybe there's two other civilizations similar to our own technologically, but each one is on the far corner of the galaxy, on the other side. We'd have no ability to communicate with them, just based on distance. And there is a fallacy of thought in this subject that, of course, if there is more than one civilization, i.e. our civilization, then the galaxy must be teeming with them, and that it's simply not a realistic assumption, but it is one that is made all too often. And even if we were able to fill in all these values in the Drake equation, we'd be leaving one part out, and it doesn't appear in the equation at all. And that is, we need a value to represent the rate of planetary cataclysms. There are 5 major mass extinction events that happened on our planet. At least that is acknowledged by mainstream scientists. One of them everyone is familiar with, the asteroid that hit the Earth that wiped out the dinosaurs. The extinction of the dinosaurs was the key factor that allowed for mammals to thrive on this planet. It's almost impossible for us to know what would have happened to the planet had this event not occurred, and how much did the rate of volcanism play in this cataclysm as well. If we take into smaller events like the Younger Dryas event, where another round of extinction of larger mammals happened, we have to start asking, how often does the Earth get hit by asteroids big enough to change what species survive and which don't make it? Between 2000 and 2013, a network of sensors that monitors Earth around the clock, listening for the infrasound signature of nuclear detonations, detected 26 explosions on Earth, ranging in energy from 1 to 600 kilotons, all caused not by nuclear explosions, but rather asteroid impacts. To put this data in perspective, the atomic bomb that destroyed Hiroshima in 1945 exploded with an energy impact of 15 kilotons. While most of these asteroids exploded too high in the atmosphere to do serious damage on the ground, the evidence is important in estimating the frequency of a potential city killer size asteroid. On February 15, 2013, in Chelyabinsk, Russia, a 600 kiloton meteor impact damaged hundreds of buildings and injured more than 1,000 people. There has been a total of 190 confirmed large craters that have been found on Earth. And when we look at the Earth being covered in mostly water, we'd have to estimate there's a lot more impacts that we haven't found or confirmed yet. Our solar system has 2 main areas of contention in regards to asteroids and comets. One is the Oort cloud, said to be the remnants of the formation of the planets, pushed out into the outer regions of the solar system. And we can conclude that it's most likely replicated on most, if not all, other solar systems out there. But there's another asteroid belt that lays within the solar system, which lays between Mars and Jupiter. One theory for this asteroid belt was a collision or destruction of a planet in between these orbits. This theory isn't fully accepted anymore, as the findings suggest there isn't enough combined mass left in the asteroid belt to point to this once being a planet. But I suggest we don't know when the supposed collision or destruction occurred. It could have been very early on in the formation of that a planet, say Mars, collided with a big enough protoform planet that was, say, the size of our moon and not formed fully yet, smashed into each other, causing Mars to form much smaller than what we would anticipate having looked at other exosolar systems. In other solar systems, we see a plethora of what is called super-Earths, large Earth-like planets where in our solar system, Mars is roughly located. In fact, our solar system seems to be the odd man out, with us not having a super-Earth. So there's a few questions we can derive from this. 1. Is there a similar asteroid belt in all, or many, or some of these solar systems? Is this unique to ours or a few, or is it quite common? If it's common, what effect does a super-Earth have on the distribution of asteroid impacts? We know that we are relatively protected by Jupiter, but if we do a thought experiment where we have Earth and Jupiter and we replace Mars with a super-Earth, would our rate of impact decrease even further? If it did, and life kept going through its trajectory in earlier evolutions, tended to favor large massive creatures, with each successive cataclysm destroying the bigger animals, would mammals have become the dominant species? Would the asteroid that killed the dinosaur even have hit Earth? Would they have evolved and the Earth look much different than it does today? You would have to lean on yes. Yes, it would. However, it's also possible that one of the other 4 extinction events didn't happen either, and perhaps it would have been a different animal to take over than the dinosaurs. Our scientists have an annoying way of suggesting that our evolution was a foregone conclusion, and that these events that shaped our life on our planet would be replicated on other planets, when, as I just illustrated, one change in the makeup of the solar system, one more or less massive impact on a planet can change the course of life on a given planet. It is unwise to suggest that a similar evolutionary process would arise as it did here on Earth. The universe could be littered and teeming with life. It may be more likely there are billions of planets of dinosaurs than with humanoids. There could also be countless other variations of beings that evolved with their specific circumstances on their world. If a world's sun has one flare too big that hits them, where ours didn't, that could shape life on that planet differently. Different levels of volcanism and tectonic activity could shape it. More or less activity, and you'd have different creatures that are better suited to survive in that environment. We simply don't know the rates and effects of cataclysms, and in general the standard rate and effect of evolution in different environments and possibilities, to really have an idea of what life will look like on other planets. While it's possible we are unique, with unique circumstances, and maybe it's a certainty rather than merely a possibility, we can't know for sure if life is destined to become like life on this planet has become. And that's my big problem with mainstream scientific community on this subject. They default to an either-or situation. Either we were destined to evolve like this, and so other beings must as well, or it was completely random. If it's random, then we really have no clue what we will find out there. Talking dinosaur creatures? Sure, it's possible. What's not probable is finding ourselves out there. We look out into the stars and hope to find company, others that are in some way like us, hopes that we are not alone. There could be more advanced beings out there with technology so foreign to us that we can't see them, even if they're flashing in front of our faces. And yet, as of today, the only example and reference we have to go on is us. It's like we're looking in a mirror that has no reflection. Okay, so now it's time for you to tell me what you think. Let me know in the comments below. Please like, share, and subscribe, and be sure to hit the notification bell. It really helps out a small channel like this. Be safe, and I'll talk to you next time.